much, Gabriel. I'd like to begin by thanking Professor Shastri and Manoj for this beautiful conference. Everything is so well organized, and the maths is very, very interesting. So thanks a lot for inviting me. Okay, so I'll be speaking about rationality and Morita equivalence for blocks of finite groups. And I'm interested in general in what the same theme that Gabriel had in his talk yesterday, namely local global questions in the modular representation theory of finite groups. But I'm going to start in a more general context. Oh, by the way, if I start breathing too hard into the mic, just tell me. Try to adjust. Thanks. Okay, so what's the setup? We have a field, K, and we consider a finite dimensional K algebra. Any algebra, as long as it's finite. And we consider sigma a field automorphism. Okay, so now I'm going to twist my algebra A. So the sigma twist of A is also a K algebra, which I denote A sigma, such that as a ring, A sigma is equal to A. And all you do is you twist the scalar multiplication. So if you have a scalar lambda and an element of the algebra A, the new multiplication, so lambda acts on A by twisting through sigma. So as rings, these two objects are the same, but the scalar multiplication is twisted. And the point of departure for me is that, in general, A and A sigma need not be isomorphic as K algebras. Because of course, they are the same thing as rings, but you may not be able to find a ring isomorphism from A to A sigma, which respects also the scalar multiplication. So this is the main point. Okay, now there's another notion. So if I have a subfield, K0 of A, then we say that the algebra A is defined over K0 if there exists a K0 algebra A0 such that A is obtained from A0 by extension of scalars. This can be understood in a more concrete way. So this is to say, if there exists a K basis, curly B of A, which contains the identity element, such that all the multiplicative constants with respect to this basis lie in the subfield. Okay, so these are the two notions, and in fields of characteristic P, these are related. So from now on, P is going to be a prime number. K is going to be an algebraic closure of the field of P elements. And sigma is going to be the Frobenius automorphism of K, which raises every element to the Pth power. Okay. In this context, we can understand twisting in another way. So take any natural number D, and you're be interested in knowing how many times do we have to twist A with sigma so that you get back something, you get back to A as an isomorphism of K algebras. That's one condition. So this is equivalent to the condition that A can be written over the field of P to the D elements. This is not a very hard lemma, but it's very useful because it's really telling you, it's a sort of computational thing. It's telling you how big you have to make your field in order to be able to write out your algebra over it. So now we make a definition. For any algebra A, we define the Frobenius number, f of A, to be the least possible D, such that A to the sigma to the D is isomorphic to A as K algebras. So this is the smallest field over which we can write A. And because I'm doing representation theory, I'm interested in a slightly different number which is related, which is the Morita Frobenius number, which I call MF of A, is the least possible D such that A sigma D and A are Morita equivalent as K algebras. If you're not very familiar with Morita equivalence, don't worry, it's really just a little bit in the background. You can just think of Frobenius numbers. Every time I say MF of A, you can think of F of A. But anyway, what does this mean? It means that A sigma D and A have equivalent module categories But again, here the point is that this should be as k-linear categories. A and A sigma are isomorphic as rings, so that as additive categories, the module categories are of course the same, but we need them to be equivalent as k-linear categories. And it's not hard to see that the Morita Frobenius number of A is always less than or equal to f of A, and this is always well defined. It's a finite. So I'm interested in these numbers, f of A and mf of A. So before we go on, let's look at an example. So again, the setup is the same now. A is algebraic closure of f bar, and sigma is the Frobenius isomorphism. Okay, so I'm going to consider the following algebra. So I pick zeta inside k cross, so it's a root of unity. And I look at the algebra generated with two generators, x and y, where the pth powers are killed, x to the p, y to the p, and the commutation is twisted with zeta. So instead of xy being equal to yx, I have xy is equal to zeta yx. If zeta was equal to 1, this would just be the group algebra of the elementary abelian group of order p squared. Okay, and then with a little bit of work, you can see that for this algebra, the Morita Frobenius number is the degree of the extension of zeta plus zeta inverse over f. Okay, it's not totally immediate. You have to do a little bit of work, but okay, and then just another example. So suppose I have an algebra whose Morita Frobenius number is 2. If I take that algebra A and take its direct product with its sigma twist, then the new algebra will have Frobenius number 1. If instead I take the algebra A and take a direct product not with its twist, but with the 2 by 2 matrices of the twist, then the Frobenius number of this new algebra will be 2. But the Morita Frobenius number will be equal to 1. So this is just to say that in the two cases, these two algebras have the same representation theory, but they're not the same algebra because you're changing the degrees of the representations. That's all. So you don't anymore have Frobenius number equal to 1, but we have one. Okay, so I'm interested in these numbers. For blocks of finite group algebras. So I think these have been mentioned recently before, but let me define them again. So let G be a finite group, a block of Kg. Actually, you can do this for any finite dimensional algebra. It's just an indecomposable direct factor of the group algebra Kg. So you have Kg, it's a finite dimensional algebra. You decompose it into its indecomposable algebra factors, and those are called blocks. Some easy facts about blocks. Every finite dimensional algebra, so in particular Kg, has a unique block decomposition. It's really unique on the nose. And each block can also be thought of as a Kg bimodule. So Kg acts on the left and on the right, and as such is the indecomposable module. These are also the indecomposable two-sided ideals, Kg. And if you start with the block decomposition, and so each factor in the decomposition of an algebra or a ring in its own right has an identity. If you set E sub I to be the identity of the ith block, then 1 equals E1 up to ER, and this is the unique decomposition of the identity of the algebra into orthogonal central primitive idempotency. We've seen this terminology. And why do you want to consider these block decompositions? Because the module category of the group algebra is just a direct sum in the categorical sense of the module categories of So my talk is really about the Morita Frobenius or Frobenius numbers of these guys here. So again, let's just start with a example. Oh, no, but before we have example, I want to say something else. Okay, so for blocks of finite group algebras, there's a useful way to think about Frobenius twists. And it's quite elementary, but it's very useful. Now I'm going to start with my group algebra KG, and I'm going to define a map on it, self-map, which just takes, so I write every element, there's a typo here. So there should not be a bracket. So this is just the alpha GG. So I write it as every element in its canonical, with respect to the canonical basis, with the elements of G. And then I leave the G's alone, but I apply sigma to the coefficients. So this is a map. Easy to check that this is an isomorphism of rings. Now, because the blocks are just are in correspondence with the central primitive idempotents, and central primitive idempotents are just actually a feature of the ring structure, the map permutes, tau permutes the blocks of KG. Every block of KG goes to possibly another block of KG. And again, it is quite easy to see that if A is a block of KG, and you apply tau to it, you get another block of KG, then the new block that you get, tau of A, this is just the twist, sigma twist. So what this does for us is that when we are talking about Frobenius numbers, or trying to compare A and A sigma, we are down to comparing two blocks of the same group algebra. And this can be very useful. It's very elementary, but it's very useful. First of all, for example, you can see, well, it may happen that if the identity of the block, so if the central idempotent of the defining the block is already, can be written over the ground field, FPG, then it's immediate to see that tau is going to do nothing to 1A, because alpha G will, all the alpha G's that appear are fixed by sigma. So tau of A will be equal to A, and then you apply that little observation, and you get that F of A will be equal to 1. And also the other, actually even more useful thing is that you can then use character theory to decide, to understand these Frobenius numbers. So one of the things is that if, I don't really explain this, but you may know that every block, as in Gabriel's talk, is associated a subset of the ordinary complex value irreducible characters, of G. And it's not, with a little bit of work, you can see that if A has an ordinary irreducible character, which is rational valued, for example, then F of A will be equal to 1. And you have to do a little bit lifting, but it's not. Maybe it's time for an example about blocks. A little bit artificial, but I just show a little bit of block theory in action. So I'm going to consider the group G, which is just the direct product of the cyclic group of order 7 with the cyclic group of order 5, and then there's a cyclic group of order 2 acting by inversion, inverting 7 and inverting in C5. And I'm going to consider the representation theory over at the prime 7. Then KG, in this case, when the prime is 7, there are 3 blocks. And you can write down the corresponding idempotents. So it turns out, because of the structure of this group, and because the prime is 7, and because acting the way it is, these blocks are all going to be supported on the C5. The block idempotents, they're all supported on C5. The first one, this is the principal block, block containing the one-dimensional trivial character. It's just the sum of the C5 elements divided by 5. The second one you have to put in these thetas and theta primes. And what are theta and theta prime? They are the roots of x squared plus x minus 1 equals 0 over x. This is not hard. If you do this sort of stuff for your living, it's easy to just write these examples down. Okay, so we have these three blocks. What are their Frobenius numbers? The first one is easy because there are only ones, zeros, and ones. So 1 of A1 belongs to F7G. So by the previous slide, f of A is equal to the other two, A2 and A3, these guys are not there. If you look at the block idempotent, we have a theta and a theta prime, and these don't live over F7, so sigma will move them. Sigma moves theta to theta prime. Sigma moves theta to theta prime, so tau moves A2 to A3. So we have that. So we can't, by totally just elementary means, say, okay, these guys have Frobenius number 1, but then if you use a little bit the theory of blocks, it's not at all hard to show that even in this case, the Frobenius number is, even though these block idempotents cannot be written over the ground field, still the block algebra can be written over the ground. So it just means that. Okay, so this is an example. Now I should also say why I'm interested in this quite odd-looking feature of finite dimensional algebras. And the motivation, one motivation, now I just like it for its own sake, but the original motivation was coming from some finiteness conjectures in block theory. So I'm going to talk a little bit about those. In order to do that, let me introduce the notion of defect group of a block. So we have A is the block of Kg. A defect group of A, I should have said, sorry. So again, here this should be a defect group of A. Is a subgroup P of G, which is minimal with respect to the property that A is a summand of A tensored with A over Kp as AA bimodule. So what is this? Takes a little bit getting used to. Remember, A is a block of Kg. It's an algebra factor, but therefore also a left and right module for itself and also Kg. Because Kg acts on the left and acts on the because Kg acts on the left and on the right, this tensor product makes sense because Kp is inside Kg, so you have this action. And then, of course, A still acts on the left and it still acts on the right, so this tensor product is an AA bimodule. A itself is an AA bimodule by left and right multiplication, and we want that A should be a direct summand of this. So these are theorems of Brouwer, and this was not his original definition. There are maybe 20 different definitions of defect groups, characterization of defect groups. But the notion is due to Brouwer. And he showed that this is a very well-defined notion because, of course, you can see that it's not hard to see that defect groups will exist, but they form a conjugacy class of P subgroups of G. So they have the same property as C log P subgroups of G. Always a conjugacy class. And also, if A is the principal block of Kg, in other words, the block which contains the one-dimensional trivial Kg module, remember the module category of Kg is a direct sum of the module categories of the blocks. So every simple module belongs to a unique block, and the unique block that contains the one-dimensional trivial module is the principal block. Then the defect groups of A are always the C log P subgroups. But if you go to non-principal blocks, you can have smaller, and we do have. Okay, and there is a close relationship between the structure of the defect groups of A the way these are embedded in G, by this is the fusion of elements of defect groups inside G, and the structure of A as a finite dimensional algebra, or equivalently of the category, of module category. And this is really the bedrock of modular representation theory, understanding these relationships in any direction. This is what we want to do with my talk. Okay, so here I'd like to give some evidence for this. So here are some classical, absolutely foundational results. So I'm saying, well, there should be a deep relationship between the defect groups and the structure of A as a finite dimensional algebra, where what is the small, what is the first invariant of the representation theory? The number of isomorphism classes of simple A modules. And as a result of Brouwer and Veit, which says it doesn't matter, I mean, you can take any finite group G, take any block of it, and if you know, and P is a defect group of the block, then the number of isomorphism classes of simple A modules is at most, well, 1/4 the order of P squared plus 1. It doesn't matter for the moment what this number is. The point here is that the number of isomorphism classes is just bounded by a function of P. Right? The underlying group is not playing anymore a role here for this. There's another, again, foundational result of Brouwer, which is that, okay, so you have A. A is a finite dimensional algebra, therefore it has a Cartan matrix, because not, which counts the multiplicities of simples inside projective indecomposables. So this, if just considering this Cartan matrix as a integer matrix with integer entries, we can talk about its elementary divisors, common, etc. And is the fact that the largest elementary divisor of the Cartan matrix is always the order of the defect. And in fact, all elementary divisors are powers of P. Okay, so I mean, this is something we would very much like to do. We would like to bound invariance of the module category in terms of the size of the defect. Okay? And this is quite hard to do in general. Okay? And there are many refinements of for example, you may have heard of this famous K of B conjecture, which is putting a better bound on this, on the first result, on the number of isomorphisms. So even around this first theorem of Brouwer and Veit, I would say there are some quite very hard and important further developments that we would like to see. Okay, I'd like to give another result of the same sort, but a slightly more modern one, which is to say that the Hochschild cohomology of A is of a block algebra of A, is also bounded by the defect group. So to make this more precise, for any natural number n, there exists an integer which we can write down explicitly, but it's complicated, so I didn't. H of Pn, depending only on the defect group and on the dimension, on the degree of Hochschild cohomology that you are interested in, such that the nth Hochschild cohomology group, vector space, has dimension less than or equal to this number. So here again, you see, you don't see the group anymore. It's just the defect group P and the degree of the Hochschild cohomology. And in fact, you can say more, a little bit more. There are only finitely many possibilities for the corresponding Hilbert series of Hochschild cohomology. And this, in fact, so this combines, so this is a result of myself and Marcus Winkelmann a few years ago, and it uses in a very fundamental way the result of Brouwer and Veit, but then it also uses some newer results. For example, the proof of Peter Simons of Benson's regularity conjecture. So that comes in there. I don't say more about this. But anyway, this is the kind of things we would like to have, where you're bounding some invariant of the module category in terms of the defect. This is one way of thinking about local global. Okay, so, well, if you look at these three things, perhaps the next slide is not going to be that surprising. Before I say, talk about the conjecture, I make a definition just to make it easier for me to think about this. So I fix a finite P group, P, capital P, and then a P block is a block of Kg for some G, doesn't matter which G, whose defect groups are isomorphic to P. So now I want to fix a P group, and I want to look over the entire world of finite groups and pick out all blocks which have that P group as a defect group. And then there's a conjecture of Donovan. I think he made it in the 1970s, but it appeared for the first time in print in a paper of Alprint from 1986. And he says that for any finite P group, there are only finitely many Morita equivalence classes of P blocks. The fact is that for any P group, there are infinitely many groups which have a block with P as a defect group, but the conjecture says that as far as their representation theory is concerned, there's not many of them. Okay, so what does Morita Frobenius numbers got to do with this? So here's a theorem. Well, I've written his and myself, so it appeared in this form in my paper, but the entire idea of using rationality or as a component of this Donovan's conjecture is due to Gerhard Hess. So he came up with this, and we used it in a joint paper, and then I sort of developed it a little bit further. Okay? But anyway, so here's the theorem. Let P be a finite P group. The following are equivalent. So Donovan's conjecture holds for P blocks. And the second equivalent condition is that you have to bound two things separately. There exist integers C of P and R of P, which should depend only on P, such that for any P block A, the Cartan numbers of A are at most C of P. You have to bound the Cartan numbers, and separately, and you have to, the Morita Frobenius number of A should be R of P. So that's, if you can do these two things, which look quite unrelated, okay, and you can do this, maybe use different methods to bound these two things, then you would get the entire strength of Donovan's conjecture. So the entire entire module category you will trap by these two things up to finiteness. Yeah, and this is not a, I mean, it's not just something that's nice and elegant. It's really useful. So this came up, I imagine, and Gerhard had the idea for this kind of thing when we were writing some papers on Morita equivalences for blocks of finite classical groups. And we gave a proof that Donovan's conjecture holds for blocks of finite general linear groups. And this is still the only way to do it. That you have to first bound the Cartan numbers separately, and then you give an argument to show that you can bound the Morita Frobenius numbers, and then you get Donovan's conjecture. So it's still quite okay, and then sometimes the assertion that C of P exists is called the weak Donovan conjecture. You could just be interested in bounding Cartan numbers, then you'll be working on the weak Donovan conjecture. And the assertion that R of P exists is now sometimes by some people called the rationality. Okay, so this is the reason why I'm interested in Morita Frobenius or Frobenius numbers. Okay, so what do we know about these guys? So now again, I'm fixing a P group, and I let A be a P block. So we can count. We can say what the Morita Frobenius or even the Frobenius number is in some cases, important cases. But it's only as a consequence of some highly non-trivial theory. So I will give you the examples here, and each of those, in order to get the final Morita Frobenius number, is really very hard. Okay? And the problem is that it's hard to say that an algebra does not have Frobenius number 1. How are you going to distinguish A from its sigma twist? They look like they are the same thing. Yeah, they're the same rings. So it's very hard to be able to actually say that, oh, these guys are different, or equivalently that they're not. But anyway, what are the cases that we know the Morita Frobenius number? If P is cyclic, so if you put a cyclic defect, then it's known that A is a Brauer tree algebra. So that means it can be, in particular, explicitly written out with generators and relations. And always you can write a Brauer tree algebra over the ground. The relations are always over, you can write it over the boundary, over FP. And so you can conclude from there that the Morita Frobenius number of cyclic blocks is 1. But of course, as I said, this is relying on the entire theory of cyclic blocks. So there's work of Brauer, Dade, Janusz, Kupisch, I should say, I forgot, Green should be there as well. 60s, 70s, people are still working around algebras. So that's one important case. If the prime is 2, and P is a dihedral, semi-dihedral, or quaternion group of order 8, then A, or rather I should say the basic algebra of A, can be computed up to quiver and relations. And again, it turns out that the relations are all involving only 0 and 1. And therefore, you can conclude that the MF of A is equal to 1. These are the results of Karen Erdmann from the 1980s, and they rely very much on Auslander-Wright. Elementary to do this. The third important case is of fusion trivial groups. I will give you a definition of fusion trivial in a second, which may not make too much sense anyway, but I'll give it. If P is fusion trivial, then there is deep theory of Buch, which tells you that in that case, the algebra A, the block algebra, will be nothing but a matrix algebra over the group algebra of Kp. So Kp is, well, the multiplicative constants are all 0 and 1. Same for matrices. So again, trivial from that to deduce that the Morita Frobenius number is going to be 1. But the first assertion is really quite difficult. This is the theory of nilpotent blocks. This is really saying, when I say P is fusion trivial, I'm saying every block that has A as that has P as a defect group is nilpotent. When is a finite P group fusion trivial? In the language of saturated fusion system, it says P admits no trivial, non-trivial saturated fusion system. If you don't know what a fusion system is, it's fine. It's not very important. I'm not going to talk about this again. But one way to understand the fusion trivial condition is that if P is fusion trivial, and P, now this has nothing to do with blocks, P is a seal, you can embed P as a seal-off P subgroup of any finite group H. You do that, then you look at the normalizers of P subgroups, and you mod out by the centralizer of the P subgroup. This is always a P group. So, fusion trivial groups have this property. So what's the example of a fusion system? Fusion trivial group C4 cross C2. Okay, so these are the three main classes of P groups for which we know the Morita Frobenius numbers, and as you see, they are always 1. Okay, then there are some other new cases. If P is a direct product of two cyclic groups of order 2 to the m, homocyclic, then we can describe the possible Morita equivalence classes of A there's only two possibilities, KP, KP semi-direct product 3, C3, and Morita Frobenius number is 1. And then we can also do it for, Charles Eaton can do it for C2 cross C2 cross C2, rank 3. And again, the conclusion is that the Morita Frobenius number is 1. And these results, these two results here, they are relying on the classification of finite simple groups and a lot of modular representation theory around finite reductive groups, in particular, parameterization of the blocks. So again, these are not, there's a lot of work involved in order to get these, again, very uninteresting statements after the fact that the Morita Frobenius number of the block is 1. You do a lot of work, through every possible machinery that you have at your disposal, and you're getting that the Morita Frobenius number is 1. I would also like to present another recent result of my PhD student, Neve Farrell. She has been calculating Morita Frobenius numbers of blocks of simple and quasi-simple groups. And using character theory and also some other deep results on the finite, on the representation of finite reductive groups, she can show the following. So if you have a simple group or a quasi-simple group, such that the simple quotient is an alternating or sporadic group, or a finite group of B type in characteristic P, or a special linear or special unitary group, or a finite group of Lie type in non-describing characteristic, which is not of type E8, and A is what's called a unipotent block, special type block, I won't define what they are, then the Morita Frobenius number is 1. Okay, so this is saying, giving very strong evidence that in blocks of simple and quasi-simple groups, we are not finding very interesting Morita Frobenius numbers. Okay? And it's saying that every block of every quasi-simple, it's not quite there yet, and maybe it's not true, because the remaining cases remove the fact that this condition that A is not a unipotent block, I think is quite challenging. But it's saying that many blocks of finite simple groups, you can write them, or their basic algebras, you can write them over the ground field. So I find that quite surprising. Anyway, so I have not shown you, so everywhere MF of A is equal to 1. Okay? This might lead you to think that perhaps there's a very exciting theorem in the background which says that every block of every finite group has Morita Frobenius number 1. This would be an amazing property of these finite dimensional algebras. But this is not true. So there's a theorem of myself and David Benson from 2007 where we produce blocks with Morita Frobenius number 2. And this is not easy because it's very difficult to make an argument to say this algebra cannot be written over FP. At least, well, I guess the methods are not being developed yet to do that. But anyway, there is one class of examples. And just to give some more information about these, the defect groups of A are elementary abelian. And in fact, they are normal in G. And they're even more simple-minded in the sense that the algebra A, from one point of view, is not complicated. It has only one isomorphism class of simple modules. The basic algebra is a local algebra. And you can describe it. You move this algebra over what's called a quantum completed dissection. Not important. The fact is that there is one class. We have one class of blocks where we can say that the Morita Frobenius number is not 1. So there is something more complicated going on. It's 2. But we don't, as yet, have any examples of blocks where the Morita Frobenius number is greater than 2. And as I said before, no known examples of blocks of quasi-simple groups where the Morita Frobenius number is greater than 1. But on the other hand, the rationality conjecture is still wide open, where you would want to bound the Morita Frobenius number in terms of just the order of the defect group. Okay, I think I have two more slides. I'm going to go over those quite fast. Really, this is just for experts. So one of the main theorems in modular representation theory is Brouwer's first main theorem, which says that the blocks of G are in bijection with a given defect group are in bijection with the blocks of the normalizer in G of P. This is going back to what Gabriel Navarro talked about yesterday. And there are many known and conjectural connections between module categories of Brouwer correspondent blocks, but we don't in general have Morita equivalence. However, if the relevant defect groups are abelian, then it is predicted that there is a weaker equivalence between their module categories. There's a famous conjecture of Michel Bouet, says that when the defect group of your block is abelian, then the block and its Brouwer correspondent, that's the block of the smaller group, their module categories, they are derived equivalence. Derived equivalence is a homological version of Morita equivalence. It's weaker, but it's still trapping quite a bit. And recently, the past 10 years or so, Joe Chuang and Raphael Ruquier have identified a special type of equivalence called perverse equivalence. And this seems to be key for the abelian defect group conjecture. So a perverse equivalence is stronger than a derived equivalence, but weaker than a Morita equivalence. In other words, we have Morita equivalence implies perverse equivalence, implies derived equivalence. And most of the derived equivalences which we have found in the context of the abelian defect group conjecture are known to be compositions of these stronger equivalences. And it is believed that when the defect groups are abelian, we will always have a derived equivalence which is a composition of perverse equivalences. So here's a theorem of myself and Joe Chuang, which is basically saying that perverse equivalence traps your Morita Frobenius number. So I put it in this form in the context of the abelian defect group conjecture. If you have a block, the defect is P, and B is the Brouwer correspondent block. And suppose these two blocks are, have a derived equivalence, which is a composition of perverse equivalence, then we can get a bound on the Morita Frobenius number, which is just depending on the automorphism, on the defect. And a corollary of that is that an affirmative answer to the perverse form of the abelian defect group conjecture would imply the rationality conjecture. I think I will stop here. Sorry, these last two slides were too fast. Yeah, so she can show that the Morita Frobenius numbers are at most 2, but she cannot show at the moment, well, whether they are 2 or they are 1. And in fact, we are hoping that this sort of perverse machinery might help to settle that. This is quite far away. Yeah. No, not that I know of. C of P, I mean, Brouwer originally predicted this, and he said that C of P should actually be just the order of P. This is Brouwer's problem 22. But that's not true. So yeah, at the moment, there's not, well, there's some very recent work of Gabriel and Gunther Mahler and Benjamin Sambala, which is now going towards trying to find some explicit bounds for decomposition numbers in certain cases. But for the moment, we just look for a bound. Nobody has such, I mean, I have not tried, and I don't know if anybody else has tried. Yeah. But there is none so far. Yeah. I mean, this is the whole, yeah. The point is that the, no, because I think it can be smaller. I mean, you know, at least from, okay, I was just talking about writing the block idempotents down, which are containing all the characters, you know. That's not enough, because that could give you too big a number. Yeah, because you can have irrationalities in the characters of as high a degree as you want. But still the Frobenius number will collapse to 1. Just take a p-prime group, for example, like cyclic p-prime group. Yeah, so no. Actually, I think mostly M of A is equal to A in block theory. It just means, so when you put the M in, what you're throwing away are the dimensions of the simple modules, because you're just comparing the basic algebra. But because a block and its sigma twist they are blocks of the same group algebra, I really don't see how you could find too many equivalences which don't preserve the dimensions of the simple modules. So, yeah, I think there's not much gap in block theory between f of A and mf of A, but I could be wrong. Or maybe it's wrong, yeah. No, I think, yeah, no, I think in that case even f of A becomes 1. I wanted to say mf of A, but I mean, yeah. Yeah, but that's not, but that's the whole point. So for example, let me just go back to the first. Yeah. Yeah, stays the one element, yeah. But you see, it's only you could have some basis which contains the one element, which when you multiply with the one, okay, well, you know, one element, whatever you multiply it with, the multiplicative constants are going to be just 0 and 1. If I take a basis element x times 1a, what is that? That's x. So the constants are just 1. That's the whole point. That yeah. Yeah, for some basis, yeah. Yeah, this is. Yeah. That would make me very upset. It could be, but I would be.
I don't want you to make me upset.
Yeah. No.